seminar speaker today. First off, I'm supposed to remind you all that there's a post-seminar reception, a PSR. This is code for beer, or not just beer. I don't know. What do we have today? Tacos? Tacos and beer. All right. Which is just over around that way. Just follow the crowd after the seminar. Everybody's welcome. Let's see. So Neville Hogan, one of the luckiest things that ever happened to me when I was in grad school, I didn't know what I should be taking, and a good friend said, "Why don't you go over to mechanical engineering and take their dynamics course?" And in that dynamics course, they taught me bond graphs, okay? And which seemed pretty cool. Hey. Sorry.
So that was an exercise in power.
Seniority. Exercise in comedy. Anyway, bond graphs. So this turned out to be amazingly fortuitous because, like 2 or 3 years later, Neville invented impedance control for as the way that robots should do compliant control of their arms. And because I had that course, I understood causality and was able to understand what he was talking about. It was amazing luck. But that was not my first encounter with Neville. Something that's, I think, more deep and important. So let's say you come through a computer science program and then they give you a robot, and so you write code, okay, and you can make the robot do whatever you want, right? So for example, you could say, I'm watching him like a hawk. So for example, your force sensor says X, you can read that, you can multiply it by something, you can square it, cube it, take the square root, whatever you want, and then send that to a motor as a desired velocity, or you can do anything you want. You're not constrained by the laws of physics, right? Now there's something a little confusing about that because computers do exist in the physical world, so if you look close, it seems like somehow physics is going to win, all right? And there's the tension between those things is kind of interesting. And you can see people that were proposing compliant control ideas that were actually physically impossible, okay? But as a programmer, it doesn't seem like that big a deal. And I think that point was made most eloquently by Neville, so I associate that with him. The results that you might be more familiar with are, for example, that if you have muscles and you want to stiffen a joint, you can co-activate these muscles, and because of the nonlinearities, that moves them into a stiffer regime. You'll correct me if I get this wrong, right? Or, for example, some muscles cross more than one joint, which might seem redundant with the muscles you've already got that only cross one of those joints. But for example, that gives you different structures in compliant control just from the way it's implemented in the mechanical structure of the mechanism itself. So these are things, all of these are observations that cross the sort of cultural boundaries of robotics. And I think that's why Neville stands out as somebody who brought robotics forward in big ways back in the day and still. Let's see, I also have a list of appointments and awards and stuff like that. He's at MIT, mechanical engineering, brain and cognitive science, I think.
Correct.
And so I'll leave it there. Please join me in welcoming Neville Hogan.
So Matt, thank you for that introduction, but I have to tell you, this now makes me even more nervous. This is what they call there's no heavier burden than a great expectation. And I'm in the mecca of robotics, and I'm nervous already. But and as you'll see, I'm still talking about impedance by the time I get to the end of this, so nothing is new. But I want to give you a perspective. This is a problem that I've been interested in for some time, and that is what I call the paradox of human performance. This is robot soccer. It's a lot of fun. Students learn a huge amount about it, about doing things, hardware. It's exciting, but as you'll shortly see, it's nothing like human soccer. This is human soccer, right? And the point that I want to make is, humans are 200 plus degrees of freedom, 600 plus muscles. These things have much fewer degrees of freedom. We have actuators like muscles, which at best give you a bandwidth of maybe 5 hertz. 10 hertz is optimistic. Typical electromagnetic actuator is easily 100 hertz. Electrohydraulic, easily a kilohertz if you try hard. You go look at communication. Neurons peak at about 100 meters a second. Electrons 1,000,000 times faster, right? Feedback loop delays, if you're working with mechatronics, a millisecond is loafing these days. You can get 10 kilohertz, no sweat. Typical transcortical loop, if you go from sensors in the body up to the cerebellum or the cortex, 100 milliseconds easily, 150 milliseconds across the cortex. That means that if you're controlling stuff through your cortical structures, that's about as hard as doing robot control through a GPS link, which is about 130 milliseconds. So that's ridiculously slow, and yet we wind up with this performance. So what's the trick? Well, with colleagues, we've been trying to figure out what might be the trick. And one of the things that sort of is obvious is that you should expect to see predictive control. That is, if you've got this slow system, presumably you've got some sort of internal model or representation, and you use that to launch behavior that's about right, and maybe you'll do corrections. But the question I want to ask is, what form of internal model is likely in biology? And this is an example. This young man is Adam Winrich, and as you can see, he manages a bullwhip, and this lady, I forget her name, but she's doing ribbon gymnastics. And if you look at a typical engineering physics model of that bullwhip, it's a flexible structure with complex internal dynamics. It's actually braided pieces of leather. It's interacting with the fluid, which is compressible and even gets into the hypersonic regime, which is where the crack comes from. And this thing is like, my sense is if you're going to do engineering models of this, you got an infinite dimensional partial differential equation that you can't solve in real time with every available computer that's on the planet. I mean, this is a hard problem. So it seems to me that, look, this is a challenging problem. I kind of don't think that this engineering style model is a good representation of what I believe is essential as an internal model in biology. And I don't think that's too surprising. The question then is, okay, well, what is the biological system doing? Well, here's some old work that we did. So the first thing is, what's the basic geometry of internal models in human motor performance? And if you think about it, classical mechanics assumes Riemannian geometry. You probably didn't even think about that. So what's the abstract geometry that's underlying motor control? And so one of the ways we studied this was by looking at haptic illusions, and that is we had human subjects interact with a very simple planar robot that with which we asked people to feel objects that were simulated. And what you find, it's been known for some time that if you ask people to feel objects, their haptic perception is distorted. It's usually called the radial tangential illusion. Radial lines are judged to be longer than tangential lines. So what that means, if I ask you to feel a rectangular box that's about here in your workspace, a rectangle like this will feel square, right? So the thing about this is that those illusions can tell you something about the structure of what postulated internal model how it may be organized. So the first question is haptic perceptual distortion geometrically consistent? So here's the experiment that we did. So if I have a consistent Riemannian geometry, what that says is that if I ask you to feel a rectangle and that rectangle felt square to you, or you judged that line 1 was longer than line 2, if I then asked you to feel a triangle that was based on bisecting that rectangle, then if 1 is longer than 2, 1 should be this, the ratio of those lengths to those angles should be the same. And for example, if you perceive that as a square, you should perceive those two angles as equal, right? But we can test those things separately, and that's what we did. So first of all, we took a simple planar robot and we simulated rectangular holes at different places in the workspace, and we changed the aspect ratio of the rectangles from long skinny ones to short fat ones. And then we did it again at 45 degrees orientation, and And that information is sufficient for you to be able to identify a metric, at least local to that space, to that place in the workspace. And there's a bunch of details about how you do that. You have to, it's easier to have people feel a rectangular hole than a rectangular block because they fall off the sides of the block and they don't fall off the sides of the hole. Minor details like that. But here's what we find. This is 8 subjects, and this is the metric, and my pointer's not working. 8 subjective circles. So this ellipse represents the path that would feel circular to this subject. Here's the average that you see for the subjects. And there's a measurable eccentricity and angle, right? Now we do the same thing, but now we do it with a triangle, except it's a simulated triangle, so you can't get at that corner. So if you're on this edge, that edge disappears. If you're on that edge, this edge disappears. The reason for that is we want people to judge the angles, not the lengths, right? So we did that, and again, you know, the data in this case was a bit more variable, but still well behaved, and you see consistency across. This is 7 subjects. You again get a measure of the metric. You get the subjective circle as an ellipse that has an eccentricity of 1.28, but a different angle. So the length and angle judgments are not consistent with Riemannian geometry. So this is a bit of a problem, right? Because all of the mechanics that we use in Lagrange's equation, in robot forward dynamics, feedback linearization, you're assuming Riemannian geometry. Well, what's the brain doing? It's at least for the context of at least in the context of haptic perception, the brain is not using a Riemannian geometry. So what else could it be doing? Well, one possible solution is this notion of internal models based on dynamic primitives. Now, this is not a particularly new idea. Stefan Schall, Stefan worked with you for a while, Chris, right?
That's right.
And I think you guys worked on some of this stuff when he was here, and if not earlier.
That was in the dawn of time.
So it's not a new idea, but I think it's powerful. And the idea is that, look, if I have primitive dynamic behaviors, they could provide a workaround to get around the problem of long communication delays. And the primitive dynamic behaviors, they should be an attractor. Any attractor could be a primitive dynamic behavior. Could be a point attractor, which would be a way to define equilibrium posture, a limit cycle for rhythmic behavior, impedance, which is interactive behavior, and lots more possibilities. And we've been sort of trying to see if this is a way that the biological system might manage its performance. And the question is, well, how would that help? Well, I can't give you a clearer answer, but the idea is that, look, I might be able to get away with minimal central control if I had some parts low down in the system, in the periphery or say in the midbrain, that were good at generating these behaviors. Then I could sort of launch them and not completely forget them, but intervene minimally. And this would reduce the need for continuous intervention despite the fact of feedback delays. But I'd be able to achieve high performance because each of the primitives is itself highly dynamic. And the idea here of the lack of need for continuous intervention is, if you think of, there are many motor skills that if you think about them, your performance goes down. And apparently people talk about muscle memory. I don't like the term, but I think the idea is this is something I've overlearned to the point where I don't try to modify it on the fly. And I think that is at least consistent. Well, do we have evidence to support this? Short answer is yes. We, meaning colleagues and I, have been using, for quite some time, we've been using very simple robots to deliver sensory motor therapy to people recovering after neurological injury, mostly stroke, some Parkinson's disease. Long story about that, I'll tell you that some other day. But one of the nice things about that approach is that you now have a machine interacting with the patient during the process of neurorecovery, and the machine comes with sensors and a computer, and so you can get measurements that are previously unavailable. And here's one of the things that we saw. This is one of our earliest studies, and we're looking at stroke patients who are in what's called the subacute phase. They've just transitioned from the intensive care unit into a rehab hospital. And then we give them this form of therapy, which is basically, it's a boring task. You ask them to reach to points, and if they can't, the robot helps them, and the robot adjusts how much it helps based on how well they do. But at different points during this 6 weeks of therapy that we provide with the robot, we do some evaluations. And among the evaluations is we take this robot, which is a fairly it's a highly backdrivable device, And we have it behave essentially like a glorified mouse. So we ask the patient to make a movement, and the robot gets out of the way, and we just record what they do. So this is a lady who had a stroke, and she's now at week 6 post-stroke. And the interesting thing is that this is actually the first week in which she was able to recover movement at all. And we're asking her to draw a circle, and you're looking at a plan view of the circle, and this is what she's able to do. And it's not very circular, but it's big progress for her, because this is the first time she's actually able to generate movement. This is the path of the circle, quotes, unquotes. This is the speed profile along that path, and you can see that it's very much broken up into chunks. She moves, she stops. Speed peaks, valleys, peaks, valleys, peaks, completely stops here. So you see a series of pulse-like movements, and they're not all very well coordinated, and they're not all terribly straight or anything like that, or even smoothly curved. But clearly this is movement. Now you come back to take a look at the same lady and do a similar evaluation. This is at week 11. And what you see now is that this is her circle. Remember, the robot's not helping her. This is just what she's doing. And it's not a perfect circle, but it's much more smooth and circular than that was. And the speed profile now, you can see it's got some fluctuations, but she's not stopping along the way. So what we're seeing is that stroke patients, as they begin to recover, the earliest movements they make are fragmented or quantized. And in fact, we went and looked at the earliest movements, and we find the speed profile. We pick out each of those speed peaks, and we fit them to a beta function that was just a convenient way to test how variable they were. And what we find is that this was a study of 20 stroke patients. For 19 of them, what we find is that the basic shape of those sub-movements is essentially identical for all patients. That's a big deal, by the way, because the patients have very different lesions. The 20th patient, by the way, didn't recover movement, but that's how it went. But very different lesions, some in the cortex, some in the deep brain, and yet the same fundamental shape seems to be showing up in all of their movements. Not only that, is what we find is that if you looked over the course of recovery, and this now includes not only patients in subacute phase, but patients in so-called chronic phase. That's people who have reached stable performance, living in the community. We bring them back and give them therapy. We also can make them improve. And what you see is, this is first therapy day, and the heavy line is the actual measured speed profile of their movement. They're making a simple reaching movement. Little light lines are an algorithm that we developed to fit sub-movements into that shape. And what you see is early therapy, first therapy day, quite irregular speed profile, lots of sort of bumps in the movement and a couple of stops. Here's last therapy day, same patient. The speed, you'll notice that there are still some, quotes, chunks and sub-movements in there. There's some irregularity in the speed profile, but much less here than here. And what we find is that with statistical significance, we find that the patients, as they recover, they make fewer of these sub-movements. The sub-movements are longer in duration, higher in peak velocity, and blend together. And interestingly enough, although there's not a whole lot of data out there, what's available looks like this is similar to the kinematic patterns you see in infants as they learn to make movements. They seem to have this behavior. I'm not really so happy about this statement because the kinematic data is really hard to come by. At least I haven't seen it. So if you know about it, I'd like to hear more about it. Also interesting is if we ask humans to make movements that are really slow, we wind up seeing a surprising limitation. So if the architecture of movement control is that you compose it of these sub-movements, there should be some limitations. So one of the limitations shows up here. We asked unimpaired human subjects to make simple movements, again using this planar robot essentially as a recording device. And we asked them to make movements, so basically back and forth. This is a boring experiment. You move to that point, move back, move there, stop, move back, stop. Ask them to do it first at comfortable speed, and then we ask them just voluntarily, go slow, at least half as fast as you were when you were comfortable, and go fast, at least twice as fast as you were when you were comfortable. And subjects can do that reasonably well. That's the only instruction we gave them, just reach, comfortable, fast, slow. And you get this is the set of movements, and they're not perfectly straight and they're not perfectly regular, but they're reasonable. And you can see that they're pretty well able to obey instructions and give us approximately 2-to-1 difference between the speeds. And what you see in the data is this is data without processing. So here's the fast, and you get this very smooth unimodal speed profile. They speed up, slow down very nicely. This is very widely seen. In fact, your paper with John back in '85. That's really going back to the dawn of time.
It does, doesn't it? It's embarrassing.
Hey, listen,
I just want to point out-
it's good data.
You were my mentor, which means by some sort of mathematic thing, you must be older than I am. I think that's transitivity or what?
Yes.
Something like that.
Anyway, this speed. So, by the way, this is the same speed profile that you saw in the spatial reaching movement. But when you go to comfortable speed, you see there's a bit of irregularity.
Those are slackers.
And when you go to slow, notice the change in scale, that there's a whole lot more irregularity. Now, before we get into any analysis, if you go look at just biomechanics, fluctuation should go down as you go slower, right? Because you're inside the bandwidth of the neuromuscular system. Inertial coupling forces that might cause deviations, they go away. All this stuff should get better as you go real slow, but in fact the fluctuations get in the increase with duration. You fit the sub-movements to this. This is so the black lines are now they sub-movement fit to the raw data. And what you see is one sub-movement fast, 3 comfortable, many slow. They are distributed throughout the movement, and it turns out that that the difference in the number of sub-movements is statistically significant. I won't go into the details. Yes?
So another result from those days was Oppin's result that the reaction time to make a circle was somehow proportional to the number of sub-movements. Do you see anything like that here, where the latency, I mean, obviously you're telling them to move more slowly, but you could have also asked them to start quickly. Is there any indication the latency jacks up with the complexity of the movement?
Don't know. Good question. I don't know. Somebody should do the experiment. But the key thing I want to point out here is, if you look at it, what we saw in stroke patients, they were completely serendipitous. And we didn't set out to find these, you couldn't help noticing them, right? The observations of poor control at slow speeds, from my point of view, that's a software limitation, not a hardware limitation, right? It's got to be something in the structure of how you construct movements. And so basically, this is a depiction, or at least this is evidence of some unique feature of the way humans construct movements. So, what about interaction? I can't give a talk without talking about impedance, right? And I think that when you look at controlling physical interaction, mechanical impedance is the key to doing that. And by the mechanical impedance, the only constraint I have is that I want to have something that maps motion onto force such that those two variables are constrained, that their inner product gives you work. Everything else is open. Well, the point I want to make here is, if you go look at controlling force, I've seen a lot in the robotics literature about force control, and the problem I have with that is that force control is not enough. So a lot of tools look like a stick that you push on, right? Screwdriver is like a stick with a funny point. You can have a cross point, or a power drill is a stick with a funny point and a motor in it. Golf club is a stick. You don't push on that one, maybe not. So the point is, a lot of tools look like a stick that you push on. Well, suppose I have a model that says, here's a stick that I'm using to push on a surface, and I'm going to assume for convenience that I get a pivot about this point, that doesn't slip. That, by the way, was the reason that the Phillips screwdriver was invented. It was part of the history of the American automobile industry, the invention of that little crosshead screwdriver which couldn't slip out of its hole. But suppose I'm just trying to generate a force axially along that stick. It's going to pivot about this point. If I get a small deviation of if I'm just generating force and this point deviates slightly, small displacements will evoke a torque about the pivot point, and that torque will tend to make this thing overturn. So if I push and I don't generate the equivalent of a sideways stiffness at the hand, the system is unstable. And not only that, but the size of the negative stiffness due to pushing goes up in proportion to the force. And a minimum that I have to have, a minimum lateral stiffness is proportional to the force I'm exerting and proportional to the radius of the stick. And if you analyze what happens when you take into account the fact that this is a nonlinear geometry, the problem gets even worse. But bottom line is, you can't just push, or at least if you simply generate force, it's not good enough. You have to stabilize as well. Humans stabilize by using things like shoulder and wrist, but I'm not going to go into that. The main point is that you've got to control stiffness as well as force. And by the way, it turns out that biological muscle has this property, which is probably the most reliable observation about muscle you'll find, which is that stiffness goes up with force in proportion. Gee, what a coincidence. Well, we took a look at that. This is some very old work, but I thought it was worth showing, and that is, I think controlling interaction is essential when you're looking at arm prostheses, and we know that muscle mechanical impedance goes up with activation of force, so in some early work we developed a control system for an elbow amputation prosthesis controlled by electrical activity of opposing muscles in the amputee's residuum. And so we used biceps EMG, triceps EMG, difference of those to set a nominal position that the limb would get to if there was no external forces. The design was quite backdrivable. We used the sum of antagonistic EMGs to set a mechanical impedance, and this gives us a kind of a crude mimic of what you get with natural movement behavior. So you can hold your arm up and you can move it to a position, but in a given position, if you co-activate opposing muscles, the limb gets stiffer. And we sort of built this into a plausible mimic of what you get with a plausible mimic of that behavior in arm amputation prosthesis. So what I want you to do is show you how that worked.
Controller B, slow speed, second trial.
So this young man is Brian Mathis, and I want you to notice that he's coordinating the mechanical elbow with the natural shoulder. And this is actually a difficult task because he has to comply with the kinematic constraint due to that. That's basically a crank arm.
I'm just thinking it's amazing. Back. Controller B, high speed. No friction, no weight.
So how is he controlling the elbow? With his shoulder?
So he's got EMG electrodes over the biceps and the residual biceps and triceps. They don't connect to anything, but they're still intact blood supply, nerve supply. We pick that signal up, rectify smooth, use the sum of activities to essentially increase the position of velocity feedback gain around the elbow, and the difference of activities to set a nominal position. So basically biceps pulls up, triceps pull down. But the key thing to see though is notice that I've got to manage physical interaction with the outside world and also with the rest of the amputee. And one of the things that this does is, in fact, part of the movement is being generated by his shoulder movement. But we chose this kinematic constraint because if he was only using shoulder, then there's a singularity at which he can't get through. Although humans are very clever and they'll find ways to get around even the, you try and make it difficult for them, they'll figure it out. But in any event, what you see is in this case, this is part of an experiment where we compared, say, velocity-based control rather than this approach. We compared 3 different types. And the basic motion control doesn't work well. One of the reasons is that it requires excessive information. So to specify the velocity profile for if I set it up so that he controls the velocity of the elbow, which is a common thing to do, then you have to figure out exactly where to reverse the velocity of the elbow as the hand moves along this crank path, and that's too hard. Whereas with this approach, basically he gets to yank and push. So he's able to do relatively simple movements, and the constraint takes care of it. So I'm able to mimic natural movement control with a relatively simple approach. Now this, as you can see, this is a lab-based experiment, and one's clinical colleagues are not impressed with the engineering. We thought the engineering was great, but clinical people, they want to see activities of daily living.
would be doing if I had them attached to my elbow. I'm really, really amazed right now.
Controller B, trial 1.
So you'll notice again bimanual coordination, and he has no problem having the machine interact with his thigh or anywhere else. You can also tell from the style of the socks that this is not a recent video.
Yeah, I can go like that.
So the main point here is that, look, among the other things that we get with this approach is we can guarantee stability during physical interaction. That just comes out of the, yes, question, and then Chris's question.
So the basic thesis is that your force control or impedance control works better than motion.
Yep.
So are you able to do experiments with this prosthetic where you try it through motion control?
Yes, in fact, that's what we did. This is old work, but we tried. One of the standard ways to control prostheses using EMG is to use the EMG to specify velocity. You do that because zero signal gets you to fixed posture. So we tried that. Doesn't work as well. Basically, what you're seeing here is deflection under load and coordination of the two arms and the natural elbow with the natural shoulder with the artificial elbow. You don't get that with velocity control. They basically tend to move to a position and hold there. But Chris's question about the squealing.
Yeah, what was that?
The squealing is this is an old style brushed DC permanent magnet motor, and when you drive it to the point where you're up at current saturation, the brushes start to oscillate, and that's the squealing. So he was working this system hard. But the point here is that, look, by controlling the effective interaction behavior, you wind up with something that seems to work at least for this kind of application. A key point that I think may have been overlooked, at least I think it has been, is that if you're talking about things that are interacting with an inertial object like the skeleton, then they have this property that I call compositionality. Basically, if you have multiple impedances, they superimpose even if the impedances themselves are nonlinear. Basically what's happening is that the inertial object adds up all the torques, whether or not they depend upon motion. Here's an example, and we can use that, I think, to simplify programming. And this is something I'm sort of stumbling around right now. So let's suppose I have a desired endpoint stiffness where this is endpoint force, this is endpoint displacement, this is a nominal place where the force would go to zero, and this is some stiffness function. And I'm going to talk about stiffness, but the same thing generalizes to impedance in general. And this could be nonlinear if you wanted, for example, if you put in saturation to limit a force. But let's keep things simple for now. I take that. If you give me the kinematic equations here that tell me how I get from configuration space to hand space, the endpoint, so x is equal to some function of theta here. This is the same value. This is the zero force position for the endpoint. This is the same stiffness. This is the transpose of the Jacobian. This, if I have reasonably good torque control, gives me a computable control law that works no matter where I am. It works at singularities because I don't have any inverse kinematics at all, right? So I can use this to drive into singularities. Now you say, okay, that's good. That's a plus. But a drawback is that if the dimensions of the endpoint space are smaller than the dimensions of the configuration space, this controller doesn't do anything about null space motion, right? If you think about it, what I'm trying to do here is simulate putting a stiffness at the hand. Suppose I made that stiffness infinite. Okay, well the hand can't move, but all the other pieces can, right? So this doesn't give me null space motion control, but that's not so hard to come by. How about if I do something, I use another effective stiffness, or it could be impedance if you want, to establish a preferred configuration. So I specify a joint torque that's proportional to deviation of actual configuration from some nominal value. As I said, generalizing to impedance is easy. This K should be positive definite. I want to have control over all the degrees of freedom. So I now take this and I add it to the previous one, and this gives me, I just add them up, right? And this gives me a controller that can manage both the configuration space and the endpoint, again with no inverse kinematics, and it works. Here's a robot. I hope you can see that that thing is going into and out of singularity without difficulty. This is based on this controller. And not only that, but we get, let's see, try this, let's see if this will work. So you've seen a lot of robots abused. This is a young woman abusing a robot. So again, you know, the machine is able to go into and out of singularities and we get good interactive behavior. At least, no, not bad for Baxter. Okay? Let's do we have more of a... So again, no inverse kinematic speed required and reasonable interactive behavior. Of course, you don't get anything for free, right? So there are some limitations. If you take this approach, what you wind up with is that you don't get perfect force control. There's always a minimum level of endpoint stiffness. So here's one way to think about it. I compute the, I assume that the joint level stiffness was positive definite, so I can express it as a compliance. Take that compliance and I can map that then to the corresponding endpoint compliance. If I avoid at singular configurations, the endpoint compliance goes to 0 independent of what you do. You got to hear, I don't care what your controller is doing, the compliance in that direction is 0, period. But if I avoid those, I can now express the effective stiffness, say, in the middle of the workspace by simply taking the inverse of that. And then the net endpoint stiffness is whatever I asked at the endpoint plus this k sub j term. So that says that the endpoint stiffness is lower bounded. So I can't get to perfect force control. But by the way, that's the same for humans. Humans don't do a very good job of giving you perfect force control. You also, on the other side, at least with this dumb controller that we're talking about here, you get imperfect motion control even when you have 0 external force, because the 0 force position due to the endpoint stiffness that I asked for is this, due to the joint stiffness is this position, which is essentially the nominal of our preferred joint configuration mapped through the kinematics. The 0 force position due to the desired endpoint stiffness is x sub 0, and what happens in between is that the system, when there's no external force, it goes to something midway between those two, which is essentially figured out by minimizing the total energy in all of the springs that you've got in the system. The system does that without you having to compute it, but you're not getting all the way to either of these two positions. So you get inaccurate motion control unless you have the endpoint stiffness very much greater than the joint stiffness, and that sort of doesn't help with your interactive behavior. So you wind up with inaccurate motion control. And my argument here, although we're still working on this, is that, well, humans aren't very accurate either. So maybe this is acceptable. Another important advantage of this approach, though, is that I can add up impedances. So I can handle 2 arms, or more than 2 arms, or fingers if you wish, but let's take a look at 2 arms. If they're connected at a common endpoint, like this, or if they're connected across an object that, and I know how they interact with that object, then the net endpoint stiffness is simply obtained by adding up stiffnesses for both arms. Controller, I write one controller for the left arm, one controller for the right arm, add them up, and I wind up with closed chain kinematics that I don't need to invert, and I wind up with a net behavior that's simply the sum of both of the behaviors. So I treat each arm separately, stick them together, and I wind up with a net impedance. We're in the process of playing with this. I don't have a video to demo it, but one of the things that lets you do is, if you want to play with the endpoint inertia of the limb, configuration is a good way to do that, but you inevitably, in a position like this, get coupling between translation and rotation. On the other hand, you do this, and the coupling terms have opposite signs, and you can wind up with a very well-behaved endpoint inertia. So I think, and I haven't done this yet, I think this sort of compositionality of impedance gives you a way to maybe make it easier to scale up from modest number of degrees of freedom to many degrees of freedom. Now, there's a weasel word in there. It might make it easier if you haven't done it yet. And okay, I'm up. So now the next question is, okay, what do I do? So I'm arguing that impedance is one of the primitives that you should be working with, and motion primitives should be used. So you need to combine them, right? So you need to have a combination of these 2 things which live in very different domains. And I'm going to try this. I don't know how well it will work. So the motion primitives reflect some sort of motion planning that's done, at least in humans, in the domain that I would associate with information processing. So the key thing is in information processing, I care about causality. By that I mean the fact that you can't get the output before the input. And I care about boundedness, that is, I can't have infinite quantities. But that's all. I have no other constraints in information processing as far as I can tell. If I go look at the impedance primitives, they're fundamentally dealing with a physically reactive behavior, and they're in the domain of moving energy around, and they're subject to numerous constraints. For example, energy has to be conserved, entropy has to be produced, and so on, right? So you've got a whole bunch of structure in the way that these pieces operate. So how do I combine this sort of primitive element with this sort of primitive element? And the answer is, I think a way you can do that is to repurpose the classical equivalent circuit. So I presume these people have a EE background. Is that reasonable? So I hope you've heard about equivalent circuits. If not, this is an idea that goes way back. This is Hermann von Helmholtz and Charles Thevenin. They developed the first version of the equivalent circuit, the so-called Thevenin equivalent circuit. Incidentally, we call it the Thevenin equivalent circuit, even though Helmholtz got there way ahead. There was another version of the equivalent circuit. This is the one that has a voltage source with a series resistance. That's Helmholtz. And
Nobody does stuff.
it is.
I'm an electrical engineer.
It is useful.
Yeah, but you just make little colored lines on screen. That's electronic.
Here on. Okay, there's also the other form, which is the current source. Americans associate with a German by the name of Meyer came up with the same idea. And it's cute that they published their papers in the same month of 1926 in completely obscure journals that neither of them had found. And these ideas were generalized to dynamics by Oliver Heaviside, which is also an interesting character. But anyway, let me move on. So what I'd like to do is I want to repurpose equivalent circuits. The reason why is because two things. One is the equivalent circuit gives you this spectacular simplification. You take, if you have linear systems, and you're looking at something through a particular place where you can exchange energy with it, all of whatever's in there, no matter how complex it is, can be represented by two components and one connection. Right? That's an arbitrary complex system, simple functional form. The other thing that's interesting is you can unambiguously identify both of those components by experimental measurements at the place of interaction. The reason I'm interested in this is that if we can make it work for the, if I can make it work, I should be able to identify its components even on a human, which has spectacularly complex stuff on the inside. So for linear systems, the key idea is that the source element is the forward path dynamics. It's independent of interaction. The equivalent resistance, called impedance, gives the interactive dynamics independent of forward path dynamics. Right? So, are there constraints on this? Here's the basic idea. It's a network of dynamic primitives. I want to take the idea and extend it out now to things that could be nonlinear. So I put my impedance here, forward path dynamics here. That gives me a nominal, what I call zero force trajectory. Subtract the actual trajectory from that. That's the thing that drives the impedance. So the equivalent sources in the information domain here shown blue. The equivalent resistances in the energetic domain. And this can be as a way to extend classical equivalent circuits to some systems with nonlinear dynamics. And it's kind of, you think it's only classical, we would use it, it's neoclassical. Other constraints. So what I've been interested in seeing, so can you do this? And the answer is yes, you can write down the equations. Are there constraints on it? And one of the important ones is that you'd really like physical systems to have the invariances that you'd expect. And I don't know if you're familiar with classical mechanics or Noether's theorem, which is a whole series of invariances that fall out of Hamiltonian dynamics. So one of the important invariances that I'd like in the context of robot manipulation is translation invariance. That is, if I move the reference frame, the interactive behavior shouldn't change. Now, in fact, this is desirable, but perhaps not available, because if I take a fixed-space robot like Baxter, well, Baxter can't do everything beyond here, right? So if I go out of the workspace, I have a problem. Even at regions within the workspace, I might have a hard time maintaining really low impedance out here, and so on. It's possible, by the way, that with a mobile robot, you may be able to do better, because a mobile robot can essentially move the base frame. I don't know. I haven't worked with mobile robots. So here's an issue. So it's very tempting to think about the ideal being a nominal force plus some dynamics around it. So this is what I call the nominal force control. And the idea here is that I'd like to have a nominal force, and I'm going to specify the actual force to be nominal force with some correction due to impedance and stiffness. And again, it's easier to think of this in terms of a simple linear spring, and this is what I've had. But now suppose I translate the coordinates and I go to a new set of coordinates, which is simply the old set of coordinates plus a constant. Substitute in, and what I find is that I do not have translation invariance. In the first place, the force source, which is supposed to be independent of interaction, now depends upon the stiffness and on the reference frame. So I've lost the separation of kinds of behavior. On the other hand, I go to nominal motion control, where I specify nominal motion. The interactive dynamics generates the forces. Here's it for impedance, and again, think of it like a spring. This is what I showed you before, force function of deviation from nominal. Now I translate the coordinates, and what I get is simply plug in, and what I wind up with is that the translated force source is identical to the original force source, the translated stiffness is identical to the original stiffness, and I've got translation invariance. So the form of this probably matters. So the message here is that if I want this invariance, I should be thinking in terms of a nominal motion, and it's something that determines the deviation, the force due to deviation from that nominal motion. And I'm speculating that this nonlinear equivalent network provides a good canonical model for dealing with interaction in general. And in that preferred form, I really have to be thinking motion, not force. So that's a bit hard for mechanical engineers to get their head around, because you really want to think about forces. And there's some problems where it seems natural that force is what you need. So for example, I've been working with Sangbei Kim on the cheetah, and one of the requirements for locomotion is that you have to make sure that the integral of the net force over a cycle has to be equal to weight. So it seems to be naturally specified in terms of forces. However, when you go look at the interactive dynamics, you still have to give me a reference point for where the spring generates force as it deviates. And in fact, this maps much better into a nominal motion with a force, with an impedance. How do you choose the impedance? Well, the assumption that I'm making so far is that learning is loosely analogous to optimization. There are lots of alternative algorithms out there. I don't know them. A lot of people in this room probably know them much better than I do. So I want to use optimization as a way to, of course, learn impedance. And the only thing I need to do to make that happen is make sure that I penalize force and motion at the same point, or at least at the point where their product would work or power. And if I do that, optimization gives me an impedance. Here's a very simple example. It's kind of dumb, but simple mass retarded by damping driven by a spring. Here's the state equations of motion, but I assume that there's a noise term added into this. I'll put that noise term in just so that I'll be able to have my optimization see the need for impedance. If I don't put that in there, this thing says, okay, minimize forces by setting all the forces to zero. So mass subject to perturbation, zeroing Gaussian white noise. Here's the interface force. It's between a nominal mass here. This is the mass of the manipulator is a mass, the object has a mass m sub n, object is mass m sub 0. Here's the total mass. I do the math. It's a stochastic optimization problem, but because I kept my model really dumb and simple, I can actually solve it. And what you wind up is showing that once the cost function includes both force and motion here, displacement from nominal position, steady state solution says, okay, make the optimal damping such that you get a damping ratio of 0.707, hardly surprising. And the optimal stiffness depends upon the ratio of the force tolerance and the motion tolerance. But interestingly enough, it's got this multiplier here, which says that what you wind up with is, first of all, the system has to be stable. That's what defines the minimum impedance. The optimal impedance depends upon the force tolerance, but it's weighted by the ratio of total mass to object mass. And that says that if you have bigger manipulator apparent mass, you need bigger effective stiffness to get the same ratio of force to displacement, which may be a little bit counterintuitive. And that got us into thinking about, well, what's Baxter doing? Right? So we took some measurements, we as my student at UCLA Law School. We made some measurements of the interaction response of different joints of Baxter. And what you find is that you go check the available data that's on the websites, WeThink's website and also the Ross website. And you get data for the inertia of the links, and it's probably pretty good. But it's actually completely inadequate because it has not included the reflected inertia due to the fact that you've got little motors, big gear ratios, and that little motor inertia multiplied by the square of that big gear ratio is actually 2.5 times the link inertia in this particular case. And what we found was that if you looked at, this is one pose of Baxter, this is meant to be Baxter looking down from on top. And we're interested in being able to use pose to modulate impedance. What you see here is the blue ellipse is approximately that of a human. The red ellipse is Baxter if you don't take into account the reflected inertia, and the big yellow ellipse is Baxter actually as it is with the reflected inertia. So the bottom line is pay attention to the inertia. So we've been looking at getting Baxter to do some real dumb tasks, and let me skip over the videos, but we've been asking Baxter to do things like feel a surface, sand a block of wood. I'll show you the videos if we have time, but here's what we get. The main thing to notice is that the apparent mass really matters. In this case, we wanted Baxter to come bump into the block of wood and just drag across it back and forth. It succeeds. I don't know if you can see it very clearly here. This is the block of wood before sanding, this is after, so Baxter can actually do useful work. This is a lot of punishment, but notice that in this case, no matter what, you have to be able to deal with the transition to contact, from non-contact to contact. There's an inevitable impact happens at that time. You'd like to be able to know what it is. Here's another simple task. Basically, Baxter's feeling along a surface. Baxter thinks that the surface is flat, but what we've done is we've set up this basically a piece of aluminum with different kinds of supports under it, so it varies in contour, and it also varies in its effective impedance, effective stiffness. And Baxter's able to manage that, and we really care about the inertia here because if you do this wrong, as you sweep across these things, it pops off the surface, which is not desirable. So the apparent mass matters. So, bottom line here is if you want to choose impedance, you can do it by optimizing, including force and motion in the objective function. That's not a big deal. The big problem so far is that the variable impedance makes the problem non-convex. And I'm not a computer scientist, but I've been told that non-convex optimization is hard. And unfortunately, as far as I can tell, this non-convexity seems to be fundamental. Though I'm glad to say that some colleagues, in particular from Stefan Schall's group from San Luis, seem to be able to tackle this problem and come up with some solutions. So I don't know how to do this, but I think it's worth looking at. So let me stop at this point. I think that you need to look at dynamic primitives for interaction as well as for motion. If you do, I think they may give you a workaround for some of the challenging physically interactive tasks, and they might help you simplify scaling up to many cruising freedom. So let me stop at that point and acknowledge the many people who worked with me on this process.
Time for some questions. You all have any questions?
Gentleman in the back, I've forgotten the name.
Rex.
Rex, yes.
So I think I got a pretty good idea of what motion primitives look like in the surface of movement. Could you maybe give us a better intuition for like what a force primitive or an impedance primitive might look like?
So essentially anything that relates motion at the interaction port to the force at the interaction port. An interaction port can either be the hand, endpoint, or it could be the set of joints, wherever you think that you're going to get energy into and out of the system. So for example, you can, if Baxter comes, for example with gravity compensation, that's basically a set of joint torques as a function of angle, right? That's essentially a primitive impedance. I can use things to drive the endpoint around. That's a primitive impedance. You can even, it's not that hard. One of the things you can do to manage redundancy is, we've done it, we just basically set a nominal low stiffness for each of the joints. You don't have to do that. Baxter has 7 degrees of freedom, so you can control 6 of them with the endpoint. And then you add another endpoint, say, at the elbow, and ask that to go where you want. So you can do this. That's another impedance. And all these things can be written as a separate relation between configuration, a motion variable like configuration, torque. It's not that difficult to add in a damping term, say a rate of change. That's easy enough. You can go beyond that if you wish. Each of those becomes a piece that you can write separately, compute separately, in parallel if that's relevant. So I don't know if that answers your question.
Yeah, I think so. It's just, they're
That's
sort of
what it
different
is.
in that the motion primitive sort of has this extended time course,
Okay?
whereas the impedance thing seems to be sort of easy.
Okay, but so remember there are multiple motion primitives as well. I only talked about these sub-movements,
Right.
so they have an iteration. Another primitive that we see in human behavior is sustained oscillation. And it appears to be a neurally distinct primitive from sub-movements. Okay, so that one has a very long time course. So the impedance, is it permanently on? Constant? Among the other things that we've looked at but we haven't implemented yet is have the impedance be a implemented trajectory of impedance. That is, have one impedance during movement. You know contact's coming up, so you change the impedance beforehand. So you sort of preset it. And we've done some experiments. I haven't had time to go into them, but we've done some measurements on humans, for example, during level treadmill walking, and that's part of what you do with your feet. So you pre-tune your ankle impedance before heel strike in a manner that I think is important for managing limb control during walking. So there's a lot less here than meets the eye. It's just if you can express what behavior you want as a relationship between torque and angle or force and motion at a point where they describe energy coming in and out of the system, do that, break it up any way you want, add them up later. Chris?
No, I'm just,
No, I'm getting nervous.
You launched several generations in this quest for making things low impedance. And I can tell you, after 30 years of trying to do that, I've given up. And, you know,
So
you
Chris,
take,
I'm sorry to hear you've given up. It's
you take people like,
there are improved designs showing up even as we speak.
yeah, you take Jonathan Hurst and all the Italians who are doing variable impedance stuff, and they're throwing their hands in the air and saying, oh, this is not even worth doing.
I'm delighted to hear that they're giving up because my colleague David Vaughn in Singapore has a spectacular design.
Okay. Let me tell you, after years of therapy where I ended up, you just gotta love your actuators and your transmission, whatever it is. If you have a heavily geared system, go with it. That means you're an accurate positioner. And all the Japanese laugh at me. They have their beautiful robots that accurately put their foot somewhere. And I have these force control things that, you know, we can't make them walk at human speeds because they don't put their foot down accurately in the right place. And then we have things like Atrius, where we're turning ourselves inside out trying to make the joints torque sources. That's crazy. They're fundamentally not torque sources. And then we try to understand how humans work. And the human actuator primitive, which I think is fundamental, and everything else is mathematical construct, is actin, myosin, blipping and doing its thing.
It's a low impedance actuator.
It's
right?
not impedance at all. Impedance is this mirage to try to make simple stories.
I think you need to go back and check your physiology. Impedance is the only thing that muscle generates. So if I take a muscle, I can force it to zero force.
That's in the eye of the observer.
I sever the tendon, so it generates impedance even though it generates no force.
Let me give you one more argument. In the computer graphics world, their quest has been to make human-looking walking. And they finally are getting close. And you want to know the trick that allowed them to do that? It's including things like the Hill model in their optimization. So the gory details of how some particular actuator, in this case muscles, works, turns out to matter a lot in making things look human-like. And I infer from that there is no abstraction.
So I'm not all that interested in making things look human-like. I'm interested in having stuff that actually works.
Yes, and my advice to students on how to do that is if the stork brings you a robot, figure out, what the mechanics are and just go with that. Don't try to turn it into something else. Either position, torque, or impedance.
So that sounds like an argument that says, well, if God had meant us to fly, he would have given us wings.
Exactly. That's entirely like,
No, I think I would prefer to go home this evening by a machine that flies rather than... Come on, Chris.
So we're entering the era of know-nothingism, okay?
Entering it?
Deep learning says, if you want to make good motion, just run your optimization over motor activation and whatever you score your mechanical output as. There are no abstractions. There are no higher level variables.
I couldn't disagree more. So, for example, we have a colleague in the audience here who's been playing with monkeys and looking at their cortices, and he's finding in the M1 in the monkey, he's finding a velocity signal, not a position signal, a velocity signal.
I worry. I lie awake at night wondering whether it's a mirage, whether he's seeing what he wants to see. Sorry.
You sound like you're on my study section.
So there's stuff inside the brain that looks a lot like representations, right? Or are you one of these sort of embodied cognition people?
It looks like neurons firing. I'm a nihilist. There's no meaning.
Well, one of the things that I think is important about abstractions is that you can use them to generalize. So you guys who do all this learning stuff, great, how do you generalize?
Well, I take this meat machine over here, and I'm a meat machine, and because we're similar meat machines, we do similar things.
That's a rather limited abstraction.
That's all there is. Other questions?
Yeah, it's hard to follow Chris, I know, but does somebody else have
Especially as he's lacerated the speaker.
I have a question, just out of idle curiosity. You're talking about human performance. You mentioned that humans seem to be imprecise in positioning tasks. And when I hear people say humans are imprecise in positioning tasks, I feel very defensive. I want to wonder, are we asking the right question?
Okay, so draw for me a circle, a perfect circle on that blackboard behind you.
Sign your name. Sign your name. No.
That's the best circle I ever drew in my life.
No, seriously.
The legend is that when Da Vinci was asked to do, Da Vinci, Sistine Chapel.
Yeah.
Michelangelo. Their time with us.
He sent to the Pope, whatever it was, I forget the name of the Pope. He was asked to demonstrate his qualification for this job. He sent him back a circle that he had painted at my hand.
Ask him to sign his name twice.
That's abstraction.
It's fantastically repeatable.
Oh, are you sure?
Yeah.
We have data.
I want to see the IRB before I go on this experiment. I can't help wondering if these whatever you call that task that fits point-to-point tasks. I just kind of wondering if that's really looking at the right thing. You look at the mechanism and how fantastic it is. You look at people hitting jump shots. Oh no, we're missing the game. From the three-point line, and I wonder what's the right way to be measuring human performance. Is it really that?
So two comments. So I completely agree that a lot of the modern neuroscience looked at really boring tasks that probably don't reflect the maximum performance of humans. When you look at the lady who does the ribbon gymnastics, that's just spectacular. She's doing stuff that's not only entire body and all this stuff, but she's managing this complex object. So a lot of the work hasn't looked at rich enough tasks to really see the true coordination of humans. On the other hand, you take really good humans, like say Tiger Woods, who's not 100% perfect.
Newspapers have observed this.
He was.
Interpret that any way you want. So I mean, there is variability. In fact, so there are those, my colleague Dagmar Stewart, one of them, who thinks that the variability is actually built in, it's deliberate, it's to help with calibration and tuning. But observationally, you ask people to do the same thing 100 times in a row, and they're okay, but there is definitely a minimum, apparent minimum level of stochasticity.
I bet if you measured people's catching performance, like a baseball player catching a ball, or we've looked at juggling and devil sticking. Devil sticking is very nice. You have the stick, the stick comes down. I bet it's very poorly fit by any kind of fixed linear impedance.
Who said impedance had to be linear?
Well, once you've opened that door, then I don't even know how to describe it.
Well, I'm just saying, here's a way to go. Take an equivalent network, split it up into a nominal motion, and then an impedance about a nominal motion, and that impedance can be nonlinear. Now, the key thing is, if those impedances are interacting with an inertial object like your skeleton, it doesn't matter if they're nonlinear, they're still superimposed. The skeleton adds up all the forces it torques. Done. So nonlinearity is not necessarily invariant. It's not easy, but
It
I admit that.
requires bits to describe. And
Why?
Okay, well then you become nihilist like me.
I said
The 0-bit description to drive the actual mechanical hardware is just let the mechanical hardware do whatever it's going to do naturally.
set the hardware up so that it gets you pretty close all by itself. I think that's, for example, what's
That, there we totally agree. And what it does by itself is not impedance.
So let me ask you, during walking,
Yes.
so we're pretty good at, humans walk with very straight legs, right?
Yes.
Much,
Yes.
remarkably so,
Yes.
much more so than any other.
Absolutely.
So how do we do that without getting shock up the backbone? So if you step off a curb accidentally,
We got more joints.
well,
More joints.
there's some clever things that we do. So for example, another thing special about humans is that we have direct corticomotor neuronal connection to the tibialis. Tibialis and the finger muscles, we have direct connection without going through the spinal cord. Now, during walking, when my foot hits the ground, there's no time for a feedback reaction. Right? That's a minimum 50 to 70 milliseconds up to the spinal cord and back. So what do? So if I'm intact and unimpaired, I pre-tune and I turn the tibialis on before heel strikes so that as my heel hits the ground, I don't slap my foot down, it rolls down and it pulls my knee forward out of knee lock. Right? So I preset the effective mechanical impedance so that good stuff happens.
You said the effective mechanics, period.
Are we not talking about words?
No, we're talking about what's in the eye of the observer versus what's really happening.
Here's another observation. Take patients with stroke. Very common to have a deficit in their ability to activate tibialis. They get foot slap. So when they hit down, they do this. As a result, they take tiny steps. They won't do a large step like that. I can describe that rigorously with mechanical impedance. You can handle it.
Other questions?
Somebody needs to step up. Let's get some other questions.
Chris and I know each other for quite some time. I'm going to tell the story about that I walk. Let's go.
No, you're not.
There's one.
So in the beginning, we talked about how even a non-stroke patient, when they are asked to move very slowly, they have a hard time having a smooth velocity. And you were saying that a solution to this is to increase the stiffness, right? I might not be getting that. Anyway, the question is, so the slower we're moving, the less damping we have. And I'm wondering if you've looked at the fact that like a larger damping might be helping with the smooth velocity.
So I think you should be careful about this. So the intrinsic damping of the skeleton, the joints, is spectacularly low in biology. So we have really, really low friction joints. You know, the hip joint, for example, is probably the most efficient bearing that you've ever seen. The apparent damping that you see really comes out of the velocity dependence of muscle force. not completely established, but it looks like the stiffness and the damping are both proportional to net muscle force. So as you turn the muscles off, the damping goes down, and so does the stiffness. So it's not clear that you have changed the effective. So the benefits of damping to smooth things out may still be available. In other words, it's not clear what the bandwidth of the system is. But if I go slow enough, I'm still inside that bandwidth. Am I making sense?
What I got is that basically our joints have a lot of grease to them, so there's just not a lot of damping.
So the joints don't have a lot of damping in them, but the muscles give you an effective damping. So you don't move the joints without stretching the muscle. And the muscle has a very strong velocity. The muscle force strongly depends upon velocity, so it looks like a damping.
Okay.
And that comes from physiology that Professor Atkinson mentioned here. So I think the main point with it's, if you ask humans to go slow, there's no mechanical reason why we can't do that, but we have a hard time. And if you don't believe me, one of my daughters tried to learn to play violin. It's a wonderful instrument when played correctly. But boy, if you don't get that, there's some special thing you do with the bowing, I'm not quite sure what it is, but if you get it wrong, it goes squeak, squeak, squeak. And if you think it's hard enough to get your daughter to play piano, to learn piano, it's really hard to get her to play violin when you hate it as much as she does. So I think the difficulty humans have moving slowly is a software problem, if that's the right word. It's not in the hardware. And that's kind of interesting. Another possibility, by the way, is stroke patients tend to move slow. It's possible that the chunks that we saw in the stroke patient may just have been because she was going slow. And we haven't been able to test that.
So there's speaking of those motion primitives, there's a whole parallel set of studies where they look at these sub-movements in terms of accuracy. So, at the end of a reach, there's a set of these sub-movements that are correlated with the accuracy constraint. And the idea behind those is that there's a long loop feedback under visual control, and those are about 250 milliseconds, which is appropriate for this visual control. Is there a way to merge what you see with the slow movement, the slow movements and the sub-movements and the accuracy constraint and maybe the visual control that's taking place?
So I think they're related, but we tested that way back where we asked people to make slow movements both in a circuit drawing task and in this. And we asked them to do it with eyes closed and with eyes open. No change in the statistics with eyes closed. So if your eyes closed, I don't see how the visual system is in the loop. Now, there's almost certainly a proprioceptive feedback as well, but I wouldn't have thought that that would have the same delay as going through the visual system. So the only thing I know is it looks like a very similar idea. Vision's not essential to get this chunky, but maybe the system uses vision and proprioception. You turn off the vision and it relies on proprioception. So I think there's similar ideas, but maybe not identical.
Since we have world neuroscience experts in the room, this argument about whether they're intermediate representations that have any kind of meaning is only going to get resolved when you find the equivalent of saccades and smooth pursuit and brain structures that in the same way for the eye movement system match each of those different behavioral primitives. And the only one I know about is oscillation versus transient movement.
But hold on a second. You think that eye movements are the gold standard? But I don't mechanically interact with things with my eyes, I hope.
That's perhaps why there are no equivalent primitives.
I think it's the other way around. I think that you had limbs before you had eyes.
And maybe they have no intermediate representations. So I turn to the world neuroscience experts in the room. Is there any evidence for motor primitives in the brain for the limbs?
Well, there's all these papers out about synergies and the way synergies work. So are those the same as primitives? I mean, you guys come from MIT where they invented frog primitives, so come on, guys.
Yeah, I'm questioning whether that really is what we thought it was.
There's a question over here, let's,
I'm not even sure if I have a question or comment, or it's just this, in this free and frank, exchange of views, I was thinking about the plant hopper, which is, the plant hopper, which is sort of an interesting, a mechanical solution where normally one might see a software solution in the body, where where if the legs don't go at exactly the same point, the plant hopper just sort of flies off into space. So rather than trying to do a neurological solution, the legs are geared. So one leg can only engage while the other leg is moving. They can only engage, I mean, simultaneously.
I'm not familiar. Sounds cool. So this is what Chris would probably call mechanical intelligence. There's no representation, so there can't be anything other than mechanical.
It's all mechanical intelligence. That's it.
well, this might be a good place for